Hello everybody and welcome back to another episode of Science with Mr. Emond. Today we're going to be looking at the pH scale and doing some calculations involving pH. Let's get started. First off, we should probably know what pH is. We've talked about this in previous courses, of course. This course we're going to be actually looking at it in a different way. So we're going to start to talk about pH as just another way to express the hydrogen ion concentrations in solution. And we already know that when you're talking about those ions, they're going to be very small numbers, such as 1.3 times 10 to the negative 3 molarity. Now, when you see that, 1.3 times 10 to the negative 3 molarity, you likely have no way of looking at that number right now and knowing whether that solution is acidic or basic. And that's going to be the purpose of today. When we convert a molarity number into a pH number, the purpose of doing that is just to give us something a little easier to work with. We know from previous courses that the pH scale goes from 1 to 14. 1 being very acidic and 14 being very basic. And what's in the middle of 1 to 14? The 7. And what is this? This is something that's neutral, like water or blood. And we can be somewhere on the scale from 1 to 14, and those numbers are going to tell, those pH numbers that we find are going to tell us whether something is a weak acid, right, which would be over here. These are weak acids, or strong acids, which are over here, or weak bases or strong bases. The further away from being neutral you are, the stronger you get. Now, to actually calculate pH, we're going to use this formula here. And all it really is the negative log of your hydrogen ion concentrations. That's it. So if we can find the hydrogen ion concentrations, which we've been doing so far in chemistry, you just plug it into this simple little formula and you find the pH. Now remember, the hydrogen ion concentrations are going to be very small, like this, and the log of such a number that's small and less than 1 is going to be a negative number. So why do you think we put the negative sign out front here? It's to give us a positive value for pH, so that it's from positive 1 to positive 14. That's what that negative sign is doing up front there. So before we get started, I just want you to pause the video here, and you're going to try to plug these H plus values into your formula negative log H plus, and just make sure that you're using your calculator properly and you're getting these values given. Go ahead and just try that out in your calculator, and when you're confident that you're using your calculator properly, you can come back to this video and we'll continue on. See you soon. All right, so hopefully that worked out for you. There's a couple things I want to notice. This one right here, this was pure water, right? That's why it gave you a pH of 7. So what do the pH values mean? Well, based off the table, we now have a few different rules we can look at, right? Numbers 1 and 4 are acids. So let's go back here and look at numbers 1 and 4. This was number 1. This was number 4. How did we know they were acids? Well, the pHs were 3 and 3.2. Anything less than 7 is an acid. What else did we learn? Well, numbers 2 and 3 are bases. How did we know they were bases? Well, here's number 2, here's number 3, and these numbers are both greater than 7. What do we notice? If the last number there, this one, is our neutral compound, what do my red check marks have in common? They happen to be larger values than this one. So if you have a greater hydrogen ion concentration than 1.0 times 10 to the negative 7, you know that that's going to be an acid. If you have a smaller hydrogen ion concentration than 1.0 times 10 to the negative 7, you know that it's going to be a base. How did I know that this one was smaller? I'm actually just looking at this negative 11 and comparing it to the negative 7. I know that the higher the negative number, what that's doing is it's dragging my decimal point back even further. So I'm going to have more zeros in front of it. In this case, I have 11 digits before my 2.5. All right. When you're working with powers of negative 10, it's not that easy for some of us. So that's why we convert to pH. We just put them in that formula, because looking at these numbers sometimes can be difficult. So that's why we convert to pH. We find it much easier to look at these numbers in your right-hand side, the pH values of 10.6, and know immediately that's a base, it's greater than 7, than to look at 2.5 times 10 to the negative 11 and know from that it's a base. It's possible, but that is why we use pH. All right, so we know acids have a pH of less than 7. The lower the pH, the stronger the acid. Bases have a pH of more than 7, and the higher the pH, the stronger the base. And neutral solutions have a pH of 7 or around 7. Let's go ahead and give this a shot. Let's calculate the pH of a 0.1 molarity HNO3 solution. So what we're going to have to do here is we're going to take out our chemistry data tables, and we are going to look at the dissociation of HNO3. HNO3 is nitric acid. So HNO3 is actually going to dissociate into your H plus ions and your NO3 minus ions. HNO3, when you look at this table, has a Ka value of 2.4 times 10 to the 1, making it a strong acid. When something is a strong acid, it's going to dissociate completely, meaning whatever this molarity was, these, because they're 1 to 1 to 1 ratios, are actually going to be the same. And so if I'm going to try to calculate the pH of this, I really already know my hydrogen ions concentrations, because it's going to completely dissociate. And I can calculate the pH value by taking the negative log of the concentration of hydrogen ions, which I can easily find without doing any math, because it's a strong acid. All I need to do at this point is type this into my calculator and find it out. Now remember, this little trick only is going to work for strong acids and strong bases. So I'm going to do the negative log of 0.01. And I'm going to find this has a pH of 2. Now a pH of 2, what is that? That's a strong acid. That's a very strong acid. Let's find the pH of a 0.01 molarity solution of ammonia. So again, I'm going to look at my table for my Ka values. Why? I want to kind of look at the Ka value to kind of figure out if it's a weak acid or a strong acid. I know I'm looking for Ka values because I'm looking for pH. We're going to get into when we use Kb values in just a few slides. So the pH value of ammonia, well, ammonia is right at the bottom of my table here. It's literally the weakest of the acids. And when I try to find its Ka value, it's actually so weak that all it tells me is it's very small. I do know that when we're talking about the acid of ammonia, we have this ammonia dissociating into our hydrogen ions and NH2. Now we're going to run into some problems here, because if I want to do the pH value, I need my hydrogen ion concentrations. This time I'm dealing with a weak acid. And whenever you're dealing with weak acids, you can't just pretend that it completely disassociates, because it does not do that, right? We actually need to use our Rice tables. So we're going to create our Rice tables, and we know that we are starting with 0.01 molarity. And this is going to be decreasing by some value. So you're going to have 0.01 minus x. This is going to be, we're starting off with zeros, and it's going to increase by some value. We don't know by how much, so we're just going to put x. And of course, this is just going to be x and x. Now when you plug this in, you're going to have your Ka is equal to your products, so x times x, which is x squared, over your reactants, which is 0.01 minus x. Now we have a bunch of variables here. What the problem is we don't have the Ka value to substitute in here to solve, because on my data table it just says very small. So we're not going to ever be able to get an actual concentration of hydrogen, because we can't solve for x without knowing this. We can kind of do a little cheeky thing, which is use the value right above it, so 1.2 times 10 to the negative 15, and we know it's actually smaller than this. So we have x squared over 0.01 minus x. Now in a previous lesson, we kind of said that this x, just this one, is so small that we can basically remove it. It doesn't actually matter. So let's go ahead and actually just wipe it out. We cannot do that for this x squared up here. If we do that, we can actually solve for x squared by multiplying this 0.01 over to the other side. Let's go ahead and do that. So we have 1.2 times 10 to the negative 15. And we're going to multiply that by 0.01. So we have 1.2 times 10 to the negative 17. What do we have to do now? Take the square root of it to isolate our x. So we are going to take the square root of our answer, and we'll find 3.4641 times 10 to the negative 9. Now I only want 2 sig figs, so let's do 3.5. So x is equal to 3.5 times 10 to the negative 9. Now this x, what is it? This x is my concentration of hydrogen ions. So now I have something to work with. But remember, we kind of cheated, because this was not the actual Ka value. Really, my concentration is going to be less than this 3.5 times 10 to the negative 9. We're going to keep that in mind. So if I try to solve for my pH value, I'm going to do the negative log of this concentration. And you're hopefully realizing now, well, Mr. Iman, this kind of seems like a lot of cheating. We are not actually finding a number. We're just kind of figuring out what it's going to be smaller than. And you'd be right. 3.5 times 10 to the negative 9. We get a pH value of let's say 8.5. What does this tell us? Is this a strong acid? No, actually, it's a base, right? It's a weak base, a very weak base. And it's so weak of an acid that it's not even in the acid range, which is why they didn't really give us a Ka value. So this number is not actually going to be extremely helpful for us, right? There must be a better way when you're dealing with weak acids that are so weak you can't even do it. And that's by doing the pOH. So when you do the pOH, you're actually going to use your Kb data table. So if you flip over in this book a little bit more, you will find another much smaller chart of the relative strengths of the bases in aqueous solution at room temperature with your Kb values. And what you're going to notice is the formula that you use is exactly the same, only instead of H plus ions, we're using OH minus ions. And OH minus ions are the standard in making a base, just like H plus ions are the standard in making an acid. For example, HCl is H plus and Cl minus, which is this is a very common acid, and NaOH is an extremely common base, and what's that? That's Na plus and OH minus. This H plus and O minus are the staples of acids and bases, which is why they're being used. Let's go ahead and try it out again, but this time properly, because ammonia really is less of a very, very weak acid and more of a weak base. So if we're thinking of ammonia as a weak base, we're actually going to do a completely different equation, which is that NH3 and water are going to react and dissociate into NH4 plus and OH minus. Now what do we know here? We know still this is a weak base. And why do I know that? Because when I look at the Kb value, it's very small. It's times 10 to the negative 5. So how do I do this now? Well, same thing. We do a Rice table. I know that I'm starting off with 0.01 molarity. H2O doesn't matter. NH4, we start off with none of it. And this, again, is none of it. What's the change? We're decreasing by some amount. We don't know how much, but we know that some of this ammonia is going to be changing into ammonium. How much ammonium are we going to get? We don't really know that either, right? So these are going to be increasing, and of course, by how much? Well, they're 1 to 1. So whatever this goes down by, these will go up by. So what do we have here? 0.01 minus x. This is just x. This is just x. You're probably thinking to yourself, this looks incredibly familiar to what we just did. What's the difference? Well, let's just keep with the similarities. We have x squared and then 0.01 minus x. But what's the difference? This time we have a number because we know what the Kb value is for ammonia. The Kb value is 1.8 times 10 to the negative 5. So we're no longer doing guesswork here. We know what the Kb value is. And now we can truly solve for x. Just like in all problems that you're going to do in Chemistry 30, this value is so small, we're just going to get rid of it. And let's simplify it that way. At this point, we can multiply by 0.01. So x squared is going to be equal to this 1.8 times 10 to the negative 5 multiplied by 0.01. And that's 1.8 times 10 to the negative 7. What do we do now? We take the square root of it to isolate x. So the square root of that number is 4.24 times 10 to the 4. 4.24 times 10 to the negative 4. So x is equal to 4.24 times 10 to the negative 4. What is this value? the concentration, well, not that one, of our OH minus ions. Why is that helpful? Because with that concentration, we can find not the pH, but the pOH. And the pOH is the same kind of format, negative log, but this time we use the concentration of OH, which we just found, 4.24 times 10 to the negative 4. You just plug this into your calculator. So we are going to do the negative log of 4.24 times 10 to the negative 4. And we get a pOH value of 3.37. All right, this is not a pH value. This is a pOH value. So what does that mean? Well, we can make use of this simple relationship, which is that our pH value and our pOH value is equal to 14. We don't know the pH value, but we do know that the pOH value is 3.37. And these have to add up to equal 14. So what does that mean that pH is equal to? 14 minus 3.37. 14 minus our pOH value is 10.6. pH value of this is 10.6. Let's go back to this. What did I say that it was? I said that it was weaker than 8.5. We don't know how much weaker, we just know it is weaker. Why did we do this? To actually get a number. Is 10.6 a weaker acid than something that's 8.4? Of course it is. Sometimes you need to work backwards. And this is going to be when you're given the pH value and they want you to calculate the hydrogen ions concentrations. And so let's go ahead and try something like this, because you'll encounter these problems. Find the hydronium ion concentration in a solution with a pH of 12.6. So we know that our pH is equal to the negative log of our hydronium ion concentration. How do we find the hydronium ion concentration? Well, we know this one, right? So we can substitute in the pH. Now we have negative log of our hydronium ion concentration. Remember that this is to the base 10. Most of you have probably taken Pre-Calculus 30. And by this point in the curriculum, you would have learned how to convert from a log function into an exponential form function. If you have something to the base of some number, that's going to be equal to some y value. In this case, what is our c value? It's 10. What is our x value? Well, we don't really have an x value. It's just the hydronium ion concentration. And what is our y value? It's 12.6. So I'm just kind of trying to identify these pieces of our log function. When you have a log function and you're trying to convert into an exponential form, what happens is you have the base to the power of your y value, and that's equal to the x. So these little numbers here stay the same. What was our c value in this case? It was 10. What was our y value? It was 12.6. Actually, it's negative 12.6. Because you probably, before you do this, you want to isolate your log. So we're going to multiply this entire side by negative 1. And what does that do? It gets rid of the negatives and moves it over here. Okay, so negative 12.6, because we want to isolate the log. And that's going to be equal to our x. And what was our x? It was the hydronium ion concentration. At this point, you can just toss this in your calculator. So these are actually pretty easy to do so long as you know how to convert from logs to exponents. And it's always just going to be 10 to the power of the negative pH value that you had. So in this case, 12.6. And what is that? That's 2.5 times 10 to the negative 13. So my concentration of hydronium is 2.5 times 10 to the negative 13. Is this solution an acid or a base? Well, I could try to look at this and figure it out, but I don't really need to. Why? It has a pH of 12.6. If the pH is greater than 7, what is it? It's a base. That's how we know. Let's try this last problem. A 0.24 molarity solution of the weak acid H2CO3 has a pH value of 3.49. I'm going to switch back to my Ka chart. Why? Because it's telling me acid, so I'm going to find my Ka. And right now I have H2CO3, and that's carbonic acid. And H2CO3 is going to dissociate into, you'll have your H plus ions and HCO3 ions. Is it balanced? 2 hydrogens and a CO3? It's already balanced, right? I needed to check that just so my Rice table that I'm going to do is using the proper coefficients. Why do I need a Rice table? Because it's telling me it's weak. Anytime it's weak, I have to do a Rice table. So what did I have to begin with? I had 0.24. I don't know this. So this is going to be minus x plus x plus x. 0.24 minus x. This is just x and x. All right, we need to find the Ka value for this. So I could just look at this chart and see, oh, there's my Ka value. It's 4.4 times 10 to the negative 7, but that's not really what we're supposed to do. We're supposed to algebraically find it. So how do you do that? Well, they gave you another bit of information. It has a pH value of 3.49. What does that tell us? Well, the pH is the negative log of the H pluses. So if I can find my concentration of H pluses, that's this value right here. Let's go ahead and try that. I know my pH value. It's 3.49. That's the negative log of my H pluses. If I move this negative sign to the other side by multiplying by -1 to isolate the log, I have negative 3.49 equals the log of my hydrogen ions. And when I do the inverse log of it, or I convert to exponential form, what that leaves me with is my hydrogen ion concentrations are equal to 10 to the negative 3.49. Let's plug this in our calculator. 10 to the negative 3.49 is 3.24 times 10 to the negative 4. .24 times 10 to the negative 4. So there we go. We have this magic number here. Well, with that, we know that this and this are the same. We can actually start to plug them in, right? Let's do that. So my Ka value is the concentration of my products, which is 3.24 times 10 to the negative 4, and this is to the exponent of 1, times 3.24 times 10 to the negative 4 to the power of 1, divided by the concentration of my carbonic acid, this, which is 0.24 minus 3.24 times 10 to the negative 4 to the power of 1. Let's go ahead and throw that in our calculator. So we have 3.24 times 10 to the negative 4 and I'm going to do a little shortcut, and I'm going to copy. And we're going to multiply that by the same thing. So that's our numerator. And now we're going to divide that by 0.24 minus that. What do we get? We get a Ka value of, let's just go with 2 digits here. So that would be 4.4 times 10 to the negative 7. And when I check my Ka value on this chart, that's exactly what it is. 4.4 times 10 to the negative 7. There we go. That's basically every kind of problem you might encounter here. Hope everything's making sense for you. See you next time. Bye-bye.
Thanks for watching, everybody. You can like, follow, and subscribe to my social medias to get notifications as soon as new content is uploaded. In the top corner here, you will find the playlist that this video is in. Watch the unit from beginning to end, and over here, you will find the next video in this unit. Keep learning, everybody. Take care.